Hi everyone and welcome. Today we will be talking about linear systems. A linear system consists of some linear equations. For example, the equations you can see here, that is a1x c1y is equals to b1. Let's denote it by equation 1 and the other one as equation 2. These are called linear equations. And if you have a couple of linear equations, let's say 2, 3, 4, 5 and so on, this will consist of a system. That is, they will form a system of linear equations. Their reason we are calling it linear because these x's and these y's, they don't have any term like x square, y square or x cube, y cube and so on. That is, there is no higher order terms. So when you plot them, you just get a straight line. That's why we are calling it linear. Now our goal is to find out what is x and y. And you can easily do it for this system by using equation 1 and 2 and appropriate substitution, but we won't be focusing on that approach. Rather, we'll focus on the approach with matrices. From 1 and 2 we can write this equation in a matrix form, and this form is like this. And if this matrix is denoted as A and this column is denoted as capital X and this column is denoted as B, then this is actually a matrix equation, and our goal is to solve for this capital X. Assuming A is invertible, the solution is pretty evident, that is x equals to A inverse B. If we do that, we will simply solve this capital X, that is a column vector, and from there we can equate each components of capital X and each component coming from A inverse B to get our solutions of x and y. Now we wrote a 2 cross 2 system. What if we had n variables and n equations? That is, we have a1 x1, let's call it c1 x2 and dot 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 dot, let's say p1 xn equals to p1, and we write a2 x2 c2 x2, oh sorry, this is not x2, this should be x1, dot 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 dot, p2 xn is equals to b2 and so on. That is, there are more equations. Again, this whole thing can be put into a matrix form of Ax equals to b, and if you just invert the A matrix, then you will have the solution in terms of A inverse B, and then you can equate each components and get the solutions of your variables, that is x1 x2 x3 dot 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 dot. Now let's try to see the geometrical picture of it. So what does this mean? Geometrically. So geometrically what happens is that if you have two equations, let's say 2x plus 3y equals to 5, 9x minus 13y equals to, let's say, 1, and assuming you can solve it for x and y, this will look something like this. Let's say this is my xy coordinate, this is x, this is y. This 2x plus 3y will correspond to some straight line. Let's denote it with the green color, equation 1, and let's denote this equation with the red color. So let's say this is the line for equation 1. and the second line will have, let's say, it will have something like this. That's the graph of the second line, and the point where they intersect, this is the solution, right? Okay, so let's try to see another picture, and that picture will consist of three equations. Let's say you have 3x plus 5y minus 2z equals to 1, 5x minus 6y plus 3z equals to 2, and 3x minus 15y minus just z equals to, let's say, minus 5. So you can see there are three variables and three equations, and we take our coordinates as x, y, and z, and we will denote red color the first equation, blue as our second, and green as the third. And in x, y, z coordinate system, this equation, that is equation 1, will actually give rise to a plane. Let's say this plane. Similarly, equation 2 will give rise to another plane, and these two planes will intersect each other, assuming there is a unique solution to x, y, and z. So as you can see, these two planes have intersected, and this intersection actually will give you a line. Let's try to mark it like this. Let's say this line. And what will happen when the third equation is used, right? Let's say the third equation will have a plane like this that goes through between both the first one and the second one, and for that it will have another line corresponding to it. So even though the picture is a bit messy, the idea is that these three planes, when intersect each other, they will give us a unique point that corresponds to some x, y, and z, and that is our unique solution. Assuming, remember, we are always saying assuming this system is solvable and it has a unique solution, because there might be cases where the system will not have a unique solution. Sometimes there will be infinitely many solutions, and sometimes there can be no solution at all. And this is the geometrical picture for the three-dimensional case. Similarly, if you have an equation, let's say, has n variables and n equations, that actually gives rise to n-dimensional planes. And every time you use, let's say, two equations to get rid of one variable, the plane's dimensionality reduces and it becomes a n-1 dimensional plane. And when all the equations are used, that is n minus n there is a n minus n dimension, that is a zero-dimensional plane left, and this zero-dimensional thing is just a point. That is our unique solution. In the next lecture, we will see when we can have a unique solution, when the system is not solvable, and when there is a infinitely many solutions. Thank you.